computer. Sorry for this. So I was introducing the speakers of today. And in order of appearance, first is Dr. Giovanni Poggiali, who is an astrobiologist and planetologist at the Lesia Observatory of the Paris Observatory in France. He's from Italy originally. He has a PhD at the University of Florence with collaboration with the ENAF Astrophysical Observatory. His main research is laboratory infrared spectroscopy. He's going to tell us more about it and how does he simulate planetary environments in his lab. And he's currently working supporting many missions, such as the MMX mission of JAXA, the Japanese Space Agency, the mission teams of NASA OSIRIS-REx, and the NASA Mars Perseverance 2020. March 2020 Perseverance. He was also supporting the Italian CubeSat mission Lizia Cube, which was part of the first planetary defense experiment that was conducted by NASA. And we also have Miss Danna Jaimes Fajardo. She's a Colombian geologist from the Industrial University of Santander. She's currently pursuing her PhD. She's at the second semester. And in her research, she's working on topics related to the geochemistry of Mars. More specifically, the conditions of the atmosphere of Mars in the past and in the possible geological processes that happen there. She also has participated in various scientific dissemination activities, and she has completed an internship at the Blue Marble Science Institute of Science. Without further ado, I would like to give the floor to Giovanni first.
Okay, so good afternoon to everyone in Kazakhstan, and good morning or good evening in the rest of the time zone. So I will start to give some of the introduction and some concepts to understand why we can speak about a geology and astrobiology perspective on Mars. Mars is really a very interesting world that we will start to explore a bit in this presentation. So if we go to the next slide. The presentation, okay. First, keep in mind there are no wrong questions, never. So I will give you some information. I will stop at a certain point, and then I will let you ask any curiosity you have, and then Danna will continue. And at the end, there will be also time for questions to me and Danna. So next slide. Our presentation will follow, let's say, a path into the exploration of Mars. So first I will give you some general information on the red planet, and I will speak about a particular topic that is related to astrobiology, that is like the search for life on other planet, in this case Mars, and then Danna will move and we'll speak about the perspective geology. So going to the first slide. Mars is a very, very strange planet compared to Earth. So if we look at the composition of the atmosphere in Mars, we immediately see that it's not very pleasant for humans and human life and Earth life, because the atmosphere is composed by nitrogen, that is also the atmosphere of Earth, but it's mainly composed of carbon dioxide, that on Earth we know it's not like, it's a product of our atmosphere, but it's not one of the main components. For the rest, the day on Mars, it's almost, let's say, similar to the day of Earth. It's just 1 hour and something of difference. Yeah, let's say less than 1 hour of difference, but the year it's kind of longer because Mars is placed a little bit far from the sun with respect to the Earth. So to do a complete, let's say, circling around the sun, it needs more time. Another difference between Earth and Mars is the presence of 2 moons instead of 1. We have just 1 moon. On Mars, there are 2 moons, Phobos and Deimos, that we know probably are formed similarly to the moon of Earth, but they are quite smaller compared to the moon of Earth. If we move on the surface, let's say the ambient environment that we found is not really let's say, similar and let's say easy to be favorable for a human being, because the surface is characterized by a very say persistent desert with this very characteristic red color that is due to oxidant in the surface. So like if we imagine like a piece of iron that is left outside on Earth, and it will start to become a little bit orange due to the oxidation. The same happens on Mars. So the surface is like a reddish desert that covers completely the surface of Mars, except for the pole where we found some ices, but it's not water ices. It's like mostly carbon dioxide ices. And the other, let's say, particularity of Mars that make it a very not comfortable planet is the presence of a huge activity of global sandstorms that in some period of like the year can cover totally the surface of Mars. And this can be also a problem for all the spacecraft and orbiter that we send to explore Mars. So going to next slide. If we look a little bit closer to the atmosphere, because that one is probably one of the most interesting part of Mars, because not every planet and solar system object has an atmosphere. There are very few, except like if we don't think about Earth, there are only Mars, Venus, and Titan, and probably a bit on Pluto. But only, let's say, less than 5 bodies in the solar system have an atmosphere. So the fact that Mars still have an atmosphere, it's an interesting feature for the planet. But if we look at the composition of the atmosphere, we immediately recognize that it's not the same atmosphere, not the same kind of atmosphere that we have on the planet Earth. In particular, nitrogen, that is the most abundant element with almost 80% on Earth. On Mars, it's less than 2%. On the other side, 96% of the atmosphere of Mars is completely saturated by carbon dioxide. And oxygen, that in our atmosphere represent 20%, 21% of the total amount, it's a minor part in the surface and in the atmosphere of Mars. So immediately we understand that something happened on Mars, something, let's say, almost catastrophic if we think about like Earth life as we know, and if we think about a planet like Earth, some process bring and move Mars in the present condition. But we are almost sure that in the past, the surface of the planet was probably very different from what we see now. And if we go to the next slide, we know that there are some, let's say, key observation that can give us the idea that the surface of Mars in the past was very different. The first one is that there is some water, some liquid water that we still know is there. It's not on the surface, it's underground. And as you can see on the left, there were some analyses made with radar from the orbit of the planet that were able to look in the subsurface and detected some reservoirs, some lakes, liquid lakes, also kind of extended behind the surface. So where the temperature is less cold, water can, probably salty water to help to not be iced, but can be still in the liquid form. On the surface, we see other elements that kind of point out different, let's say, different stage of the planet Mars. In particular, we observe the presence of clay minerals. Clay minerals that were observed with infrared spectroscopy, so using infrared radiation from the orbiter, but also from the rover on the ground. Clay minerals are very important because we know that only one process can generate clay minerals from other kind of minerals, and it's like the presence of liquid water. So the fact that on Mars, we still nowadays observe clay minerals means that in a certain moment of the history of the planet, there was liquid water on the surface. the fact that liquid water is still present nowadays, there was probably abundant liquid water in the past, it gives us another perspective on the possibility that Mars, in a certain period of its history, was an habitable planet. When I speak about habitable planet, it doesn't mean that on Mars, in a certain moment, there was life, because we have to make a difference between let's say inhabited planet and habitable planet. When we speak about inhabited planet, it's like Earth. It's a planet that we know is hosting life. And for now, we know only one planet that is inhabited, that is Earth. When we speak about habitable planet, we mean a planet or like a space bodies that was probably and is probably able to support life and to support the origin of life. So Mars probably in the past was very different from the Mars that we know today. So if we go to the next slide, some, let's say, reconstruction put on the surface of Mars very extended oceans, and probably some of the craters that we see nowadays in the past were lakes. Danna will speak about a little bit more about this, because we are now exploring one of these ancient lakes on the surface of Mars inside a crater. So if Mars in the past was able to support life, this means that we can look nowadays for the trace of this life. And this is what we call biosignatures. Biosignatures are all the trace of past, present life. And sometimes we say also future life. So the fact that we see material that can form life in the future. This is not the case of Mars, that is going, let's say, toward the end of history, but in general, when we speak about biosignatures, we speak about the trace of past, present, and possible future life. So if we go to the next slide, okay, when we look for biosignatures, so for the science of life, there are a lot of different features that we can look for. Normally, the most common biosignatures, so the most common sign of life, are like the presence of organic molecules. So molecules that are containing carbon, that are like the molecules that are at the base of Earth life. But we know that organic molecule can form in the universe also without the presence of life. We see organic molecule, for example, in meteorites and asteroids. So it means that some process produce organic molecule, and then this organic molecule is used by life. So we cannot just look for organic molecule to look for life. We need to put next to the presence of organic molecule the presence of other kind of biosignature. For example, sometimes life can alterate the presence of certain isotopes. So isotopes are elements with different number of neutrons normally in the nucleus. So it's an element that remains an element for the physical properties, but is sometimes a little bit heavier than the original element. So life can alterate the presence of isotopes, so these kind of strange atoms. And if we look for certain patterns of these isotopes, maybe we can think about the presence of life. Also, life can produce some mineral. We know that on Earth, there are some minerals that are produced by the presence of life. For example, we know some carbonates that are produced by the deposition of a lot of, let's say, life sediment. So imagine in the sea, if there is a lot of shells and all these shells are like sedimenting on the bottom of the sea, we can form there some carbonates thanks to the let's say the material, the hard material composing life being. And the last one that is probably the most easy to see is the morphological biosignature. That on Earth, it's like the presence of fossils. So if we look around on Earth, we see presence of fossils. So we see the remaining of some form of life form, but also we can look for more, let's say, tricky form of biosignature that are the microbial mets. So the presence of a lot of microbes can alterate the rock and the sediment in the rock and leave some trace in the rock that we can recognize as like the remaining part of living being. To complicate the situation on Mars, where the atmosphere is very thin, we have a strong irradiation on the surface. So all the biosignatures that are on the surface are strongly altered by the presence of a strong UV radiation. So no matter which level of level of cream or solar cream you use on Mars, you will get burned every time. So the surface is completely sterilized by the presence of ultraviolet radiation from the sun, but also in the subsurface, some more energetic particles, so accelerated particles like the one that we found in the accelerator on Earth, like in CERN and other accelerator, can penetrate the surface to centimeter or even meter level. So we need to know how this biosignature can be affected by the process that we know are active on the surface of Mars. So going to the last slide, just to give you an idea of how we can work on the surface of Mars and in laboratory on Earth to understand this. Let's imagine the rover Perseverance that Danna will describe after. But for the moment, let's say let's take a rover on the surface of Mars. This rover is making some observation, and we have data from this observation. In order to interpret the data from this observation, we can go back on Earth. We can go in a lab. We can simulate the same environment that we found on Mars. We can use some material that we think are probable presence on Mars, and then we look at the outcome of the action of the environment on Mars on this analog sample. If the result that we see in the laboratory is matching the result that we see taken from the rover or the orbiter, we are quite confident that we found the same material on Earth that is analog to the material that we are observing on Mars. And this can give us a lot of information on how which is the probability of finding some kind of a biosignature. So if we study the evolution of biosignature on Earth, we can see how this biosignature can be affected by the environment of Mars. And maybe we know already from lab simulation that all the biosignature on the surface of Mars are completely destroyed. So we are not going to look for the biosignature on the surface of Mars, but every time we are looking for biosignature in the subsurface of Mars. So Perseverance, as Danna will say, can go in a certain depth, and in the future, ExoMars, the rover from the European Space Agency, will go in the most, let's say, in the deepest depth, having reached by a rover that is 2 meters, in order to go like where the high ion irradiation from the galaxy is not arriving. So next slide, and I stop here. If you have question, otherwise we can proceed to the second part.
Thank you, Giovanni, for this first part. We don't have questions yet. It could be that people need some more time to think of them, or it was that you were very clear. So I think we can keep on continuing with our presentation, and Danna can take over, and we give people more time for questions. Thank you.
Okay, so sorry. Just as Giovanni was saying before, he was talking more about the astrobiological aspect about Mars. I will explain the geological part of Mars. That is what I work with. So as he was saying, we have right now rovers that are on Mars collecting data that we can use to understand what happened on Mars in the past. This is the rover Perseverance that is currently on G0 crater on Mars. And we sent this rover there. Well, I mean, we, like humanity, we sent that rover there because we considered that there was a lake at some point. And as he was saying, liquid water, usually it's kind of information for finding life in that part. So Perseverance is more like a rover that is looking for life. more than actually a geological rover, but he's still like collecting geological information, okay? Those are the tools that Perseverance has. They are really diverse. They are looking for different aspects. And if you look at SuperCom, this is the tool that is being used for looking for the chemistry, minerals, and like describing the rocks that are present there. So this is not the best geological rover that we have on Mars nowadays, but his mission is more related with looking for life or presence of life in the past of Mars, and also he is collecting samples because the next step will be returning rocks from Mars. Nowadays, we don't have rocks from Mars. The only planetary body that we have rocks from besides Earth, it's the moon. Okay, so we are looking forward to return rocks from Mars that will be really useful to finally understand which kind of minerals we have in the surface of Mars, which processes has been affecting these rocks, what generate these rocks. That are the questions that we usually ask as geologists about that. So this is like a cool picture of what they think it's going to look like when the rocks return from Mars. We can obviously not send yet humans to Mars, but this could be a very first step to understand better the conditions of Mars nowadays. So if we don't have rocks from Mars and we cannot go to Mars yet, how can we study the geology of the planet? We have three different steps that we can take that are kind of similar to what Giovanni was describing before. So we have the data that the rover is sending daily or monthly or whatever. We have different rovers on Mars, and all of them are sending pictures, spectra, and different information related to the minerals that we have in there. And on Earth, we can do two more steps. We can do laboratory experiments where we can simulate the conditions on Mars. So as we were seeing before, Mars has different atmospheres. Mars has different temperatures, different pressures. So all of these can be simulated here on Earth, and we kind of know which rocks we have there, so we can expose those rocks to the conditions that we have on Mars and see what we can expect to discover what we can expect from Mars. On the other hand, we have the modeling. So modeling basically make reference to using computer softwares to recreate the conditions on Mars and see again what we can expect. Those two sides of here are basically what I'm most related with, and I will make you
Danna,
a short
Danna, we are
introduction of
losing
what I.
sound. If you could maybe switch off your camera to liberate some bandwidth.
Okay. Mm-hmm. Okay. So here it's a short explanation before about the geological features that we have on Mars. So here first you have the Earth, like the geological time scale of the Earth, so you can have an idea of the times that we are managing on Mars about the geological history of Mars. Here you have the geological time scale for Mars. So as you can see, on Earth, the steps or the size that we have taken are like more related with the present. On Mars, they are more related with the past of Mars, and it's because the interesting part of Mars, or the part that we care about, or where maybe the water was present and life was present, it's the very past of the planet that is basically in here. The most recent time of Mars doesn't seem that interesting to scientists for now, at least. And here you have the different geological processes that can affect Mars. So first you have volcanism. First, for volcanism, you have crush formation. That is basically when a planet it's forming, it's originating you have a lot of volcanic activity because the planet is basically like melting in the surface. Then you have the formation of the biggest volcanoes like Tarsis, that's one of the most famous regions on Mars, where it's the Olimpo Mount, that is basically one of the highest volcanoes in the solar system. And then you have like more um, general volcanic activity. Another important factor is the impacts that we have in the planets. This is a really important process at the beginning of the solar system because you can imagine it is like building planets with with Legos.
I think there is a problem with the microphone of Danna. If she can hear us. If not, may I ask Giovanni if you can take up a little bit of the slide until
Yes,
she can
yes. I don't have the control of the slide, but I can say a few more words. So let's say from okay. So I can have
Sorry for that. You can share
No,
maybe
no.
your copy of the
Yeah,
presentation
I'll share it.
until Danna is back.
Sharing it now. Let's see. Can you see the presentation?
Yes.
Okay. So let's say when we want to construct or to assemble, as Danna was saying, like a planet using the geology, we have to think about like all the possible effects of the environment in changing the geology of a planet. So, for example, these are the experiments that Danna is doing and using, let's say, different process, and like sometimes we can see how this geology can be affected by the process. So, for example, like if we look here, controlling the pH, so the acidity of the environment, the redox state, so how much oxygen we have at exposition for reaction of oxidation, and then the presence of ions. And of course, these are like linked with the presence of water in the. Okay, Danna is here.
Yeah, hi, I'm sorry, I lost
Let's go.
connection for a moment.
I think it's still a good idea to
Yeah.
keep the camera
Okay.
off.
Yes.
And I'm not sure that Danna is able to continue at the moment.
Okay, so we continue. So when we look at the experiment that we can do in lab, actually we can recreate the same condition. This, as I was saying, it's like valid for okay. Can you hear me?
Yes, but we lost the presentation.
Okay, let's go. Okay. It's just okay. Okay, good. Can you see?
Yes, yes.
Okay. So as I was saying, like we can, we have to think about all the possible process and all the possible effect that we that can affect the surface of Mars on the planet, and we try to reproduce this effect one by one or all together on Earth in order to interpret the geology of the planet and like how the planet evolved with the history, with the geological history, so on millions or billions of years of like in the solar system. In particular, what we need to well understand is that when we speak about geology and when we speak about like a planet, in some way we know that the planet itself is not a static object most of the time. Like planet like Earth, we know that it's geologically active, so there are some event and some process on the surface and inside the surface that are changing the aspect of the planet. So if we have in the past of Mars the presence of water on the surface in contact with a surface that was, or a crust that was geologically active, that it's probably like not anymore the case of Mars, but could be in the past of Mars. So the presence of water in contact with an active surface and an active crust can lead to a series of events. So we can see here in this graph some of these. So the presence of like movement and tectonical movement on the surface, or a subduction zone in which some material is like entering in the interior of the planet, and some material on the other side is exiting from the planet. This can lead to or in this way, some material can exit from here and then it's like recycled on the other side. So this can lead to some evolution and some also mixing between the interior of material and the exterior material that will alterate the surface. And if there is water, the material can start to react with water. So there are a lot of questions that have to be taken account. Which was the parental rock, so the rock in the origin of the planet that then started to be altered by the presence of water, which are or which were the geological settings. So now we see Mars and we see like some state of the planet, but we know and we have to retrieve which were the condition of the planet in the past. This is the only.
Sorry,
Okay.
can you hear me now?
Yes.
Okay, thank you.
You can take over.
Yes, it's fine. The most important thing that I want you to understand today is that you can think about minerals as you think about people. So minerals have like some temperatures that they prefer, just like some people prefer summer over winter or winter over summer. So the rocks are kind of the same. The minerals have temperatures under which they are formed. So the temperatures are basically related with the components that are present in the rocks. On the other hand, when we are cold or when we are warm, what we do is we try to dress properly to that temperatures. So on winter, you will use sweaters, you will use scarves, you will use coats or whatever. The minerals obviously cannot do that, but they will try to adapt their structure, their chemical composition to this kind of new temperatures or new pressures, or sometimes the presence of water is something that will really generate like an unstable moment for the rocks. So this is what I'm trying to show in here. As Giovanni was saying, the picture in here shows the different processes that happen on Earth. And as you can see on Earth, we have plenty of options of geological options in here, but it's not the same for Mars. Mars is not this active as it is on Earth nowadays. So we are trying to understand how the rocks, like the diversity of rocks that we have on Mars, that is not as diverse as Earth, but still kind of diverse, how they got formed without this tectonical settings that we have here on Earth. For instance, the subduction zones that creates the recycling of the surface of Earth doesn't happen on Mars. And we still find some rocks on Mars that kind of suggest these processes of recycling. So we need to understand which process really happened and if there are other geological settings that maybe we don't have on Earth, but we had someday on Mars, and that can be useful to explain how those rocks were generating. This is basically what I do. I'm doing like modeling for figuring out this, but I'm pretty sure that in the future, with more data, with more information, maybe with rocks from Mars, we can be able to figure out what was happening in here. As I said before, or maybe Giovanni said before in the previous slide, we are not completely sure about the composition of the water on Mars at the past. If we have water, we are not sure about the composition of the water on present Mars if we have water again. So it's really important when you are doing a modeling to figure it out what kind of elements you have in the water. Well, now that I say water, maybe you're just thinking about the water that you drink and the water from the sea, maybe if you have go and see the sea before. But water is much more than just H2O. Water has also other elements like, I don't know, potassium, sodium, calcium, and depending in the concentration of those elements and depending also in the atmosphere of the planet, depending on the pH of the water, you will have different conditions. So this is what we're trying to understand as well. We're not completely sure about the conditions, but we have some clues, as we are not completely sure about the atmosphere in the past of Mars. Just as Giovanni described at the beginning of this presentation, we know the atmosphere of nowadays of Mars. That we know, that we have the data, but we don't know how that atmosphere was in the past. And it's impossible to go back to the past and figure out what atmosphere exactly we had. But we have clues. There are the minerals. And that's what we will use in order to understand which processes happen on Mars. So I'm just saying all of this so you know that there's plenty of research still to do on Mars in case that you are interested in that kind of topics. There are a lot of questions that we still don't know the answer. And yeah, it is just science. It's how it works. There are small steps that you take, and then you combine all those steps and try to explain the history of the geology of a planet, in this case of Mars. And that's it. Really sorry for the problems with the connection, but yeah.
No
It's time
worries,
for
no worries,
questions.
Danna. Thank you both for your contribution. Actually, we have some questions in the chat. They just came directly to me, so I'm gonna ask them to you. One is for Danna, I think has to do with your comment about rocks are like people. So there is a person that asks, Azar, he's asking, what would happen to rocks if they are in temperatures they do not prefer? Let's take a temperature, like a rock that is formed in volcanic procedures, and then it's formed with high temperature, and then it comes out to the cold. Let's take this example. What happens to it?
Okay, so you can think as we were saying about a rock or a mineral that it's created at really, really high temperatures. And then they go to the surface of the planet, like here on Earth. So when they get exposed to these kind of temperatures, what will happen to the mineral is that it will probably change. It will be now another mineral. So we have minerals that are called alteration minerals, that are basically those minerals that are generated in the surface of the planet at temperatures that are like, I don't know, 25 Celsius degrees, that it's like nothing. It's like a surface temperature, very different to the temperatures in the deep air that are like 1000 Celsius degrees in the very deep. So what will happen basically, it will depend in what you have. If you have water, then maybe you have more elements, it will create a mineral. If you don't have water, but it is just getting exposed, it will just create another mineral with the same elements. So yeah, it will basically be another mineral. That's the short answer for that.
Okay, and there is another question that is to Giovanni, I think. It's about, or to you as well, but it has to do with the sample return that you mentioned, I think, in the first part. So the question is, when are we going to have a sample from Mars? When is it estimated?
Can I answer? Actually, the, let's say, optimistic plan is to have the sample not early than 2035, I think. But the let's say the plan is really changing. I would like to say year by year, but it's mostly month by month, because as you can imagine, the effort to do such kind of campaign is huge. It's like a joint campaign of ESA and NASA, so US and Europe. So the sample collected by Perseverance now are closed in some special tubes. These tubes some are still with Perseverance, some are deposited on the surface of Mars in some strategic place. So the idea, there will be a lander that will arrive there with a little rocket ready to like send the sample in orbit. So in some way, the sample have to go to the lander. At the beginning, there was the idea of another lander devoted to collect the sample, but they will like there will be problem in doing another lander. So at a certain moment, like following the success of Ingenuity, the helicopter delivered with Perseverance, that was like breaking every record and flying, like it was supposed to fly 5 times, it's like more than 70 times. So at a certain point, someone was like, okay, we can use helicopter to collect the sample and bring back to the to the lander. Now the most realistic thing is that Perseverance, that hopefully will like have the same history of Curiosity, that was like the rover that is still active. If Perseverance will continue his activity for like tens of years, like we expect, Perseverance itself will deliver the sample to the rover, to the lander. At that point, the sample will be sent in the orbit of Mars. Another spacecraft will arrive, collect the sample from the orbit, and bring them back to Earth. So as you can imagine, it's like a really, really complicated plan that for now, it's like optimistically seeing sample coming back around 2035. So in like 10 years, something like that.
Okay, thank you. There is another question from Sulamita, who has been following us from the beginning, and it's actually she wants to ask about liquid water, what it is. I think that Danna mentioned that we don't know what type of liquid water was on Mars in the past, and we don't know if there is liquid water now and what is the composition. Could we say some hypotheses? Like, what do we think? Is it a salty water? What are the hypotheses for such water, like the liquid water on the planet?
Yeah, first, I think I would like to start describing that water as any compound um, can have 3 different states. So it can be solid, that it's ice water. You can have it as a gas, that is basically vapor of water, and you can have liquid water. So the liquid water, it's an state in which the water can be useful for life. That's why we usually look for liquid water. Now, water can have different compositions. So it can be salty, as the seawater, for instance, but you have fresh water, that is the water that we actually drink. If you go to a river and you see that water, it will be different from the water from a lake and from the water from the sea. So that's what I mean when I describe different compositions of water. For Mars, we don't know, but if there is water nowadays on Mars, I know that it should be salty, because somehow the briny waters has like more possibilities of being liquid under lower temperatures. At least that's what we think.
Okay. There are more
If I
questions. Yes,
can add
sure.
just an information that we didn't mention, but nowadays the temperature range of Mars, it's really, really different by what we have on Earth. On Earth, let's say the greenhouse effect is like kind of stabilize the temperature on Earth in a regime that is not so cold. So like 0 degrees, okay, we have on Earth 0, -20. I think the coldest temperature on Earth is -40 something, and the highest is like 50 probably, something like that. On Mars, the highest temperature that can be reached is like less than 20 degrees, I guess. In August at midday under the sun, when we have 50 degrees, and the lowest temperature is well below 100 degrees. So we need that something is like preventing this water to freeze if the water is liquid. And probably salt is like the most obvious conclusion.
Okay. Thank you. So we have some more questions. This comes from Alina, who asks, what do you think about water which came from meteorites? Is it possible if water came from meteorites, does it mean every planet has water on it from this source?
If you
I
want,
guess I can start and then Giovanni can complement my answer. Yes, actually, water came from meteorites. There are two possible sources of water in every planet. It will be from meteorites or it will be from the gases inside of the planet that go out from the planet by volcanoes. So volcanic activity and meteorites are the two sources of water. And yes, water is actually a very common molecule in planets, in every planet, but the situation is that life doesn't need just water. Life needs liquid water. And for having liquid water, you need temperatures that allow you to have this water. So that is where is the detail. There are a lot of moons here in the solar system that has a lot of icy water. So they are full of ice. There are also some planets or yeah, like solar planet body systems that are called icy planets, icy moons. They have plenty of water, but it's not available for life as we know the life. So that's like the situation. It doesn't, not because you find water in a planet, it means that there will be life. You need certain conditions to make this water useful.
Okay, but also regarding, as you said, like for the origin of the water, the meteorites are a source that we take into account for
Yes.
planets,
Mhm.
right?
Absolutely.
Actually, there is a nice way to trace the origin of water, because as I was saying at a certain moment, like we know the existence of isotopes, so like atoms that have like some additional neutrons in the nucleus. So the properties of the atom is not changed, but the atom is different from like the original atom. So we know water, that is like oxygen and hydrogen, but we know like deuterated water, that is like water with the deuterium instead of hydrogen, where deuterium is like an atom of hydrogen with like one neutron in the nucleus. So it changed a bit the mass of the atom. In this way, we call it also heavy water, the water. But it not change. It doesn't change the properties of the water. So let's say, as I was saying, like isotopes can be a tracers of life, but it's also a good tracers of the origin of like elements in the solar system. So looking at the ratio between the deuterated water and normal water, we can look at which distance from the sun like an object formed. And we know nowadays that, for example, comets that in the past were believed to be like the most probable source of water because they're rich of water, they have a ratio between deuterated water and normal water different from Earth. So they are not the source of water. So nowadays, the idea, as Danna was saying, like that asteroids and meteorites that are like more dry, but they still contain some water, are the most probable source of this water, with the like addition of the water that was already in the structure of our planet and just degassed from the interior to the surface.
Mm-hmm. Okay, so there are some more follow-up questions. I think we have, if you have like a few more minutes in your time, we are past our official duration, but some people are asking. I would take two questions. One is if we know how the atmosphere of Mars has evolved during the years, like if we can tell this by the minerals, possibly?
That's a really good question for the person that asked that question. It's the question we have tried to answer all this time. We still don't know yet. We have some ideas, that is what I'm going to mention, but it will probably change during the next years. So yes, minerals can tell us kind of how the atmosphere evolves, because the minerals will reflect how much carbon dioxide, for instance, you have in the atmosphere. They will reflect the pressure of the atmosphere. Something that I think we didn't mention is that the atmosphere of Mars, it's really thin in comparison to the atmosphere of Earth. So we know that for sure that if Mars has warmer temperatures at the beginning, it was because the atmosphere was thicker, and not just that, but also the atmosphere should have been like with enough for doing a greenhouse effect. So we know that Mars lost the atmosphere. We don't know how, we don't know when exactly, but it should have been at the beginning of the history of Mars. That is when we stopped seeing the most remarkable clues about liquid water in the surface, because for having liquid water in the surface, you also need a thicker atmosphere. So that's what I think we know for now. But yes, it's a really good question, and it's something that we still are not sure how to answer that. Thank you for the question.
Okay, that's good. I mean, I know that a lot of times from my own research that they combine the stellar evolution with the atmosphere, like to know what is the early activity of the sun, how did it strip out atmospheres with its radiation and plasma from Mars. So this could be, it's a composite question. You're right.
Yeah,
We
and also
have, yeah.
depends like the mass of the planet, like the fact that Mars is like way more small than Earth, and so the gravity of the planet is very small compared to the Earth, is one of the factors that probably triggered the loss of the atmosphere. Not the change in the atmosphere, but the loss, the fact that nowadays the atmosphere of Mars is very thin.
Okay. I have one question that is a bit complementary, but I think it's quick to answer, which is uh, by the time that these rocks from the sample return missions reach Earth, are we sure their composition would not change? How do we ensure this?
That's another extremely good question, and that's something that scientists are going to start working on right now, or I think there are some projects currently going right now, because yes, the rocks will probably change because of I mean, if they will travel from Mars to Earth, they will be encapsulated, and in this encapsulated place where they will be, the conditions will be different from Mars conditions. So yeah, they can change. We don't know how, and as far as I know, there are not still many publications on that, but it's something completely that we will need to understand. So yeah, thank you. You are doing really great questions today.
Also, one help can be the fact that among the tubes on Perseverance, there are some tubes that are called blank. So they are like tubes full of like particular material that they will be not used. They just travel to Mars. They will stay there with the sample and they will come back. So we will, knowing what was in that sample, we will know what was the effect of course, going there and coming back. But
Okay, that's
if everything goes well, because like for that case, we need to have that sample back. Instead, as Danna was saying, we can also perform on Earth some experiment in order to understand how like irradiation and temperature and like vibration during the departure and arrival on Earth can affect the sample.
okay, interesting. And last question, I think, is from Christian Schwartz, who is asking, what kind of experiments should we do now on Earth in order to help us understand better the whole the Mars environment? What can we do on Earth for this? Experimental wise, like a laboratory.
I think the most important experiment that we can do for now is to understand, let's say, for example, for Perseverance, that is, as Danna was saying, is devoted to the search for life. So the sample collected are high value for astrobiology. we need to understand, like, on one side, if what we observe with the instrument on Mars is like what we think. So there are some observation also of like some particular compounds, sulfates, organic probably. So we need to know if that observation are, let's say, what we think they are. So we have a signal from an instrument. We have to create a sample on Earth that, like, it's an analog sample, and then measure it with the same instrument, so the copy of the instrument on Earth, and see if we obtain the same signal. On the other side, as Danna was saying, we have to perform, and it's pivotal to perform experiment to understand how this sample changed on the surface of Mars, just sitting there on the surface, because they were like under the surface, and now they are exposed in a tube, of course, but it's not like being like 10 centimeters behind the surface. Now they are like just covered with like 1 centimeter or even less metal tubes, and how the travel back will affect the sample. So the experiment on Earth are like are not like substitution of going to Mars. They are a support of going to Mars. So we go to Mars, we look everything around, and then we perform experiment on Earth in order to understand if what we are observing is what we think in reality, or if it's something else.
Regarding this, you mentioned about analog samples on Earth. Is it what these analog field studies that we hear about are also concerned with, like to gather rocks on Earth that are similar composition to what we think we observe on Mars?
There are actually two kinds of analogs on Earth. One is like finding on Earth environment that are close to Mars for composition. I would say it depends what we are interested in, of course. But for example, a geological analog of Mars is finding a desert on Earth with some conditions that are similar to Mars, and collecting sample there in order to have a complex sample in an analog condition, so analog environment. On the other side, knowing some information on the geology of Mars, we can just create our synthetic analog, mixing together single mineral collected on Earth in order to have something similar to the surface of Mars. Of course, this is not a natural analog. It's not collected somewhere on Earth. It's like assembled in laboratory using different compounds, but then will be more close to what we observe on Mars. And then using like analog biomolecules, so organic molecule that can be present on space, because we know they are like in meteorites or in the interstellar space, and we can use them as an analog of what we expect to have as organic content on Mars.
Thank you. I think we have answered a lot of questions. There are more. So I would like to ask you if you could show your last slide where you had your emails with Danna.
Can you show the slide, Giovanni?
Where someone can contact you for all these questions. And yes, I can also share it, I think. Yes, I think Giovanni is sharing it. Okay, so I'm writing it also on the chat.
I think you are mute, Giovanni, if you're, yes.
Well, just saying, feel free to send any question.
Yeah, same for me. If you have any question, just
also like related,
email.
let's say, not only on Mars, let's say, we are pretty open to answer also question if you have question on like your future career, if you want to like start a career in research and you have question on like how it works, feel free to send.
Okay. Yes, I see people are thanking us. So that was a nice presentation we had today. I'm gonna stop the recording here.